Hey everyone, in this video, let's go to question 797, all paths from source to target on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, we're given a directed acyclic graph, DAG, of n nodes labeled 0 to n-1, and we want to find all possible paths from node 0 to node n-1 and return them in any order. The graph is given as follows, where graph at I is a list of all of the nodes you can visit from node I. Basically, there's a directed edge. You can think of this as like an adjacency list, right? Representation. Okay, so before we even start this problem, let's take a look at the wording here, right? Like find all possible paths. Whenever you see something like that, right? Like find all possible or generate all possible combinations, all possible permutations, etc. When you have an exhaustive search like that, it's often good to use recursion. But not only that, backtracking. And we've done this in many of our other problems like subsets, permutations, combination sum, etc. But whenever you see like generate all or find all, backtracking is a good approach here. And I don't want to just like say like all, if you see all, just generate, do backtracking. Like think about like why it makes sense, right? Because this question in itself is actually not that hard if you know like how to work with it. So just take a look at the graph that we have over here. And I'm actually going to do the paint version that I have. Okay, ignore this like, ignore this part right here that we have. Okay, so let's say like we start off at 0, right? So then what can we do? Well, we can go through 0's neighbors. So we go through 1, and then we go through 3, right? And then what? Well, once we're at 3, we have nowhere else to go, right? So then we go back, and then let's say from here, like we have nothing. So that's why I kind of added in this. But let's say from 3, we go back to 1. So what are we doing? We're backtracking back to 1, and then we go to 4, and then we go to 3, and then we backtrack to 4, and then again we backtrack to 1, and then we backtrack to 0, and then we go to 2, and then we go to 3, and then maybe we backtrack to 2. Maybe there's like another edge that something like this. Maybe this is like something like 5. So we go here. Obviously, these numbers are not correct because it should be like 0 to n-1, but yeah, like hopefully you get the idea. But notice how like we're going to the final location, and then we're backtracking and seeing if there's anything else. So that's kind of like why backtracking might make sense here. And for all of these questions that we do, like we have a general format that we like to follow, right? So we have a result variable, we have our recursive call, and then we return a result variable in the very end. Our result variable will be basically filled with all of the set of paths that we can form in the helper function. So let's take a look at like how we might want to do this, right? So the first thing I think we need to do is handle the case where graph is empty. Well, if graph is empty, I don't know if this is like even valid, but let's just assume it is. Then we return an empty list, right? Because there's basically no paths to form. Otherwise, well, let's just declare some variables here. What is n? N will be the length of the graph, right? N will be the length of the graph that we have here. What else? Okay, so we're given graph in terms of something like this, right? But this is not really useful for us. It'd be better if we can somehow represent this using like an adjacency list. So in Python, it's very easy to create. We just create a default dictionary where it's a dictionary that points to a list, right? So like every key points to a list. And then we would just go through the graph like so. And then we will do adjacency list at I is equal to graph at I. So basically all this is going to be doing, it will be mapping something like 0 to 1 and 2. It'll be mapping 1 to something like 3. 2 will be mapped to 3. And then 3 will be mapped to empty like this. Okay, so now let's take a look at like how we might want to code in our helper function, because the way you do this is it's just as you expect. You would just go through this like one by one. So we start off at 0, we go to 1, and then a recurse, we'll go to 3, and then we'll see there's nothing here, so we'll backtrack. There's nothing else here, so we'll backtrack. We'll go to 2, and then we'll go here, and then we'll go here, and nothing more, and then nothing more, and then end. So that's kind of like how we want to do this. So let's take a look at like what we might want to pass in. So as with like all of the problems, our general format stays the same. So always want to pass in the graph. What else? Well, we need to pass in the result, right? So this is like what we will add. We need something else as well. We need cur, right? We need to keep track of where we are. So for example, if I'm at 0, then I'm at 1 here, and I'm at 3. Well, I need track of this path, right? So that'll be stored in cur. Cur will be added to res. What else? Well, we need our adjacency list, right? We need to know like adjacency list. What else? Well, we need to know like our base condition, right? Our base condition is when we reach the final node. Well, we need to know what the final node is. So we can pass in something like n to represent our final node, right? So we have that. Now, what else do we need? Well, I don't know. Do we really need anything else? If you think about it, do we really need anything else? I don't think we do in this case, right? Because cur, we can always find like the last element that we've added in cur, right? We can just look at like cur and like -1, and we can check if that like is equal to n. So I don't really think like we need the like anything else here. So maybe let's just go ahead and start with this and see where we can get at. So let's take a look. Okay, so we can check if cur at -1, if we've just added in n-1, right? Like if we added in the n-first item, if this is the case, then we can add this cur to our res. So we will do res.append cur. And remember, we always add in a copy when we're doing these types of questions. And then we can just return. And that's all there is to this. Cur at -1, this is like our last item that we've just added. Okay, what else? Well, if we didn't do that, then cur initially is just like this zero here, right? Because initially, like we'll always start with the 0. So we're passing the 0 here. So now we need to know, like the neighbors that we can visit. So I can do for neighbor in adjacency list at cur at -1, right? So this will be the item I just added. So it'll be adjacency list at 0, which is just 1 and 2. And now this is like where backtracking comes into play. So when you're exploring 1, we'll first add 1 to our list. We add in the neighbor. We'll do our helper function call. And then simply we'll pop it, just like so. This is how we always do our backtracking. So why do we pop it? Because when we are over here, like let's say we go to the number 3. So at this point we have 0, 1, 4, 3. Well, let's say there's another connection here. Maybe there's something like 6, right? Well, I don't want to have that 3. Like I don't want it to be 0, 1, 4, 3, and then like 6 and then 3, right? That doesn't make sense. Well, we need to remove this 3, which is what we do in pop, and then we do 0, 1, 4, 6, and then 3 again. So that's like why we pop it. Just what the subsets question or permutations question to understand like why we need to pop it. So we have that, and then here, what do we need to pass in? We have graph, res, cur, we've already adjusted here. Adjacency list, we don't need to change. But n here, again, n does not need to change. Okay. And that's actually, I think, pretty much all we need to do for this question. So let's actually pass in what we need. The res, and the cur is like an empty list. Adjacency list is something like this. N, we can pass in n here. And what is actually n? N is the length of the graph. So let's actually go ahead and try this out to see if we run into any problems. Okay, so list index out of range. So I wonder if it's possible. Oh yeah, because I need to include some value here, right? So I need to include like the first value here. So that's why we can refer to the last value. So we can do something like this. Okay, it passes. So now let's go ahead and click submit. And it also passes. So perfect. So again, just to kind of explain like why we need to append and then pop, it's because if we have something like our path is, let's say 0, 1, 4, and then 3, right? When we are at 3, and then we are like out of the loop essentially, or not out of the loop, we're basically done the function. So we go back to this one. Well, when we're over here, we still have 3 as part of the list, right? Simply because of how lists work in Python. They persist even if you go back a recursive stack. So here, if we were to then go to 6, then we would have something like this, which is not what we want. We need to remove this 3, which is why we do the pop. And then this is how we come by this final answer here. So that's exactly what we're doing here. And so this is how we do this question. As for a time and space, it's often like actually pretty hard to tell for these types of questions, because when you generate like all types of paths, you have to know like what are like the total number of paths you can generate in like an arbitrary type of graph. So it's a little bit difficult to check here. You can check in discuss if you want to learn more. But yeah, as for time and space, just check and discuss, and that should be good. Okay, thanks for watching.